Good morning. Today's lecture I'm going to discuss about transducers. So in this lecture we are going to cover what are transducers, and what are the types of transducers. And also we are going to discuss about some applications of transducers. So these are the main topic that is going to be covered in today's lecture. So let us start with the basic definition of transducers. So a transducer can be defined using this particular simple schematic: input, output, and we have a device that is called a transducer. So what is a transducer? It's something but it's a piece of instrument, or it is something but a device. That device is capable of transforming a signal from one form into another. For example, if you have light energy or light input, and this light input, there are some cases where we want to transfer into a signal which is normally in the form of some other form. For example, in the case of electrical output. Now, suppose we have temperature, and the temperature then we can transfer into in the form of electrical output, like speed and so on. So there are many physical signals. That signals are these signals we can transfer into what we call an output form or electrical form by using what we call the transducers. So transducer is, the word transducer comes from the transduction, because there is some energy conversion is going to take place there. So depending upon the type of the energy conversions, we have various types of transducers are available in the market. So now, if you look at any kind of instrumentation system, it is going to be one of the critical element. The transducer is going to be one of the critical element. For example, if you look at instrumentation system, and in this instrumentation system normally consisting of an input device, I'm talking about a very general instrumentation system. Of course, it is receiving various input signals. Then the second stage normally we call as the signal processing unit. Followed by we have an output unit. So any instrumentation, any general type of instrumentation system, in its simplest form, we'll find these are the main elements. The first element normally called as input device, and this input device is supposed to transfer the input signal or the input energy into a signal that the signal processing unit can accept. So this device is nothing but a transducer. Okay, then once the signal is transferred from what you call a physical form into electrical signal, so what you're going to get it is in the form of what? Electrical signal. Now this electrical signal will feed into a signal processing unit. The signal processing unit, as simple as, like, it could be an amplifier, can be filter, right, maybe an attenuator, etc. It can be of any of this kind. Then finally the output unit again needs some kind of conversion, because in most of the cases the output unit is also the output may not be in the form of electrical output. It can be in the form of a display, or it can be some kind of movement or something like that. So definitely again it's another type of transducer we're supposed to use. Now that's why sometimes we also call the output unit is also called inverse transducers, because we want the electrical signal that is to be transformed into another form of signal. Now let us look at one example here. Suppose I have the voice recorder system, for example. So voice is input, and it is normally a physical form of energy, or this is something but voice due to the vibrations. So it's a belonging to the what you call an acoustic, or it's a sound signal, and this sound signal supposed to be transferred into electrical signal by the help of the transducer, and that's transducers normally we call as microphone. So if you use a microphone is capable of transferring the signal into minute signals, minute voltages, and this voltage it won't be able to display. I mean, to obtain from an output device like a speaker. So what we need is the microphone output has to be amplified, and also need some filtration, because there are some cases where we want to get rid of some of the signals, unwanted signals, which is normally we call as the noises. Now the microphone output signal will be passing through the signal processing unit. The signal processing unit, sometimes it may amplify the signal, it may filter the signal, and some cases it may attenuate the signal, and there are many corrections. Sometimes we need offset correction, and so on. So there are many signal processing operations that is need to be done. Then the output will be given to what we call another unit, which is the output unit. Probably it is a mic, for example. So this is speaker, for example, speaker. So the output unit we are going to use a speaker. Again, the speaker is another type of transducer where you are transferring. I mean, say inverse transducer, where the signal that is received by at the output unit will be transferred into what we call a voice signal by the help of what we call a speaker. So this is a voice recorder. You record it and you amplify, you filter it, then you can get it again, reproduced by the help of a speaker. This is a basic idea about an instrumentation system. So again, if you go back to the basic definition of the transducers, transducers are the piece of instrument, and these instruments are capable of transforming any form of energy into another form, one form of energy into another. And most of the cases, the transducers has got input in the physical form, and the output is in the form of what we call the electrical form. Now we are discussing. Now we will move on to the second subtopic, which is the classification of transducers. The transducers are basically classified based on the following. The number one in this particular slide, you'll find transduction principle. The method that is involved, what kind of transformation that is going to take place. So sometimes what happens, the input energy that are converting to changes of the resistance. It could be changes in the capacitance, or it could be changes in the inductance. So the transduction principle, or maybe because of the input energy, some level shifting is going to take place, or maybe some kind of extension is going to take place. So transduction is how this particular input energy is transformed into the electrical form. What is the principle behind? So likewise, there are a lot of classifications that we are going to see in detail. Second one is talking about primary and secondary. The primary transduction, the transducers, and secondary transducer difference is, normally in the case of primary transducers, they are capable of transforming a physical form of energy into another form, may not be electrical form. So for example, if you look at a Boron tube, okay, suppose we look at a Boron tube, and if there is a pressure in, this is the pressure input. Because of the pressure, what is going to be, it is going to stretch. Okay, this particular Boron tube is supposed to stretch like this, and from this probably can connect another device. It could be a potentiometer, or maybe another like a LVDT. Suppose we have an LVDT here. Suppose we have an LVDT, and anyway, this LVDT we are going to discuss in the coming class. So this is the core of the transformer. So what is going to happen, because of the pressure, this Boron tube is going to stretch, and this stretching or the extension, or the deformation that is going to happen in the Boron tube, this Boron tube will make some corresponding changes is going to be taking place here. So if you look at this one, this particular part where the pressure energy, or the pressure that is converting into the pressure the pressure input that is transformed into some kind of mechanical displacement. So here, these type of transducers normally we call as the primary transducers. So they are transferring one form of energy into another, but that is requiring another stage where they can be transformed into electrical signal. So in this example, this is called the secondary transducers. So the pressure in this example is supposed to be transferred into what we call a displacement by the help of a primary transducer followed by a secondary transducer. So this is another example for another classification, that is primary and secondary transducers. Third classification about passive or active. From the name itself is clear. One is passive device, which is not requiring any amount of, any input energy, and the actives are requiring some amount of energy or some energy conversion. Power boosting, or some energy conversion is going to take place there. Or in other words, I can say that in the case of passive, there is no input energy is required. It's a passive component, so it requires additional amount of additional circuit. That circuit is can transfer the transformed signal into a voltage level or something. To be more clear, the passive transducers are normally, there are three types basically. They are in the form of resistors, or maybe in the form of capacitors, or maybe in the form of inductors. So in these cases, in this particular example, the value of the resistance will change according to the input signal. In this case, the value of the capacitor may change with respect to what we call the input signal, and here the inductance value will change depending upon the input energy. So in this form, all the output are getting in the form of either resistance, capacitance, or inductance. That's the reason they are also called the passive. And this type of signals, in order to do further signal processing or something, we suppose to transfer into voltage or current signal by the help of additional circuits. On the other hand, in the case of active circuit, the output are already in the form of what we call voltage or current signal, so it can be directly connected into the signal processing stage for further amplification or something. So passive, normally in the case of, the passive transducer produces output in the form of resistors, capacitor, or inductor, whereas the active transducers normally they will produce the output in the form of either current or voltage. Okay. Now the third classification is talking about the digital or analog type of transducers. So the whether it's a digital or analog or digital. So there are transducers which are available in the form of an analog output. For example, if you are using a tacho generator or tacho motor or tacho, normally that can be used for the measurement of speed. So suppose we have a motor here and whose speed has to be measured. So in order to measure it, we are going to couple a tacho generator here. So this is supposed to be a tacho generator. Assume that this motor is connected to 12 volt DC, and the motor is running at certain speed. Suppose it is running. This is already coupled with a tacho generator. And if you suppose to give, if you connect one instrument, a voltmeter, so it will be able to measure the voltage, and this voltage is something but is proportional to the speed at which this particular motor runs. So here the output is in the form of analog signal. Now the same technology, the same the speed that can be measured by a digital device. For example, if you are using a slotted wheel sensor, where suppose we have got a slot here, and there is one transmitter at this side, and we have got a receiver here. So what is going to happen is this wheel is rotating at certain speed. So this wheel is supposed to be attached to the same motor shaft, and this wheel is rotating. Okay. So what is going to happen is at a particular instant, the transmitter, receiver, and this particular the slot all comes in particular line, or they have become collinear. As a result, what happens? The light will pass from transmitter to the receiver, and will be considering as a digital pulse. So every revolution, you will have one digital pulse. So one digital pulse is correspond to one rotation. So this digital pulse can be counted by using a digital counter. So again, in this case, the output is in the form of the pulses. Therefore, the output has, this type of sensors we call as digital sensors. Now we are going to discuss about further classification of transducers. So here the main classification we are talking about the resistance based transducers. So the input will be a physical form and output will be in the form of change in resistance. So these type of transducers, the main common types of transducers are potentiometer transducers, strain gauge transducers. The strain gauge sometimes can be also called as gauge or gauge, hot wire meters, resistance thermometers, thermistor, and photoconductive cells. In all these cases, the input will be a physical form and output will be the change in the resistance. Okay, so we are going to discuss each in detail. Potentiometer sensors, strain gauge sensors, hot wire meters, resistance thermometer, thermistor, photoconductive cell. So this is the potentiometer sensor. So we have got input. This is the biasing voltage or the input voltage EI, and assume that the total length of the potentiometer is L, and Xi is the what you call the wiper. This part is basically called as a wiper or the movable part. So this is the variable part actually, because now to this particular wiper we'll attach a vibrating component here. So when the vibrating component, this component is getting vibrated, then what's going to happen is that this wiper also will be moving, up and down. So depending upon the vibration of what you call this component, you will have the corresponding change that is going to happen in the wiper. So accordingly, you can find some output here. As you know by normal equation, the potential divide rule, EI is the input voltage multiplied by Xi over L. So this will tell you the output voltage. Okay. So if you are interested in the Xi, which is supposed to be the length or the vibration, the distance between the wiper point or the contact point, the wiper point with respect to ground, Xi is normally calculated by the equation E0 divided by EI multiplied by L. And this E0 divided by EI is supposed to be a parameter like what K into L. So we can say that Xi is a function of the total length of the what you call the potentiometer. So this particular device can be used for measuring the vibration. So we can attach that vibrating component to the wiper. As the device or the system vibrates, then automatically we will find the output voltage here. So this is the simplest type of the potentiometer. This can also be available in the form of, it can be also available from the angular form. So the same concept can also be applied to the wiper. So in this case, the wiper will be a midpoint here, and these two will be connected, as we have seen here, will be connected to EI, and the output normally will measure across here. This is the E out here. It can be measured, and of course, a moving object can be attached to what you call this wiper, and that will make the different E out, and so you will be able to measure the total E out. These type of sensors are very common, very simple to use actually, because the reason is that the components are very simple. The connection wise also there is no complicated connections. So what is required is we have to have a potentiometer, input voltage, and the corresponding output voltage can be measured by the help of a voltmeter or instrument. So the next sensor we are going to discuss is the strain gauge. The next type of transducers is the strain gauge. As you know, in mechanical we have the basic terminologies. One of the terminology or one of the concepts is called the definite. One of the basic concept is stress. Okay. So the stress is nothing but the force applied over area, and its unit is Newton per meter square. And when you apply a force, there must be something called strain, and this strain is defined as the change in length to the original length, or change in area to the original area. So that is normally indicated by strain, and normally strain has no unit because the numerator as well as the denominator have the same. It's like a ratio, so there is no unit here. So this strain can be measured. Okay, mechanical strain can be measured by using a device called strain gauge. And if you look at the strain gauge structure, it is nothing but a resistance material, and of course it has got a backup. A base plate will be there, and these are the terminals will be out. We have got two terminals, and this material is something like a supporting or backing material. For the purpose of support, and this is the what we call a tiny wire. So this is the basic principle of a strain gauge. So what is going to happen is we are going to apply some stress or some force on this particular material. What is going to happen is that there is an expansion or the deformation is going to happen. So there's a deformation is going to happen on this particular material. So that deformation will make some change in the resistance. As we have studied in the basic electricity, R, resistance of a material, can be calculated from the equation rho L over A, and R is the resistance in ohms, rho is the resistivity, which is in ohm meter, L is length, which is also in meter, and A is area of cross section. So the resistance of a material will be dependent upon these three parameters. So one is the specific resistance of the resistivity, which is depends upon the material. The next quantity is the length, and the third quantity is, or the third variable is area. So it is resistance is inversely proportional to area and directly proportional to length. So when there's a force is applied on this particular strain, the strain gauge or this particular instrument, there is some changes is going to take place. It can happen with area or maybe with length. So that will give rise to change in the resistance, and this resistance change, which is directly proportional to the strain. Now we are going to look at the gauge factor. This is one of the important questions normally put in the exam, which is called the gauge factor. So the gauge factor is nothing but it is one of the specification of a important specification of a strain gauge. It is defined as del R by R or dr by R, dr divided by R divided by del L by L, or can be dl by L. So this is the change in resistance to the original resistance, and this is the change in length to the original length. Now as we studied before, or as we have mentioned before, del L by L is nothing but the strain, and that strain is normally indicated by a notation epsilon. So the same equation can be rewritten as del R by R divided by epsilon. Now in order to prove, in order to get into a final equation in terms of physical dimensions, so we are supposed to start with a small derivation. As we studied already here, R is equal to rho L divided by A. So we are interested in del R, which is a change in resistance. To do that, we are supposed to do the total differentiation. So we are going to differentiate each term by assuming that the other terms are constants. So for example, I am going to differentiate first rho, keeping L, A and A constant. So this is going to be, I will get what? D rho. You can also mention like dou rho or d rho, or the partial of dou, plus now I am going to keep L as constant, sorry, L as a variable, so rho by A is going to be constant. I will get L, plus next I am going to consider rho L as constant into differentiation of 1 by A. If you differentiate 1 by A, we will get dA over A square with a minus sign. Because derivative of 1 by x is minus 1 by x square. So the next term is that we are supposed to divide the same equation by R. So we will get L by A d rho L by A, because every term is supposed to divide by R. We substitute R here, but we substitute the equivalent of R, which is rho L by A plus rho A dl divided by rho L by A minus rho L divided by rho L by A times dA by A square. So what is going to happen now? This term, this will be cancelled. This will be cancelled. We end up with what? D rho by rho plus this is cancelled. This is cancelled. We'll get dl by L minus these two terms cancel. We have what we call dA divided by A. As you know, area, normally area of the cross section of the wire. So as we know that A is equal to pi d square by 4. This is the area over DC diameter. D is the diameter. Assume that we have, this is the size of the cross section of the wire having a diameter of D. So if you differentiate this equation, dA will get pi by 4 into 2D into dd. This is where we are going to get it here. So this is the equation of A. So what is dA by A? Pi by 4 into 2D dt divided by pi d square by 4. This is cancelled, this is cancelled, this term cancelled. We have 2 into d by d. So dA by A will get an equation. Let us say this is number 2, and already we have an equation here which is supposed to be number 1. So which is supposed to be dA by A. That value is substitute in. So we substitute 2 in 1. We have dr by r is equal to d rho by rho plus d by L minus, this equation is going to be 2 into dd by d. Okay, now let us assume that this equation is number 3. Now we try to recollect one of the basic fundamental equation, which is called the Poisson's ratio for material science. The Poisson's ratio is defined as mu equal minus del d by d divided by del L by L. So which means that change in diameter to the original diameter to change in length to the original length, that is normally called as the Poisson's ratio. So that Poisson's ratio we can we'll get the value corresponding to what we call del d by d, and that we can substitute here. So from that Poisson's ratio we try to find out what is del d by d or dd by d, because that equation can be, this equation can also be written as dd by d divided by dl by l, both ways fine, minus. So if you find out the value of, from equation we can find the value of dd by d is equal to minus mu into dl by L. This is, let us say, fourth equation. So the fourth equation we substitute in 3. So if you substitute 4 in 3, we'll get dr by r is equal to d rho by rho plus dl by L minus, already we have minus and we have one minus here, that makes it plus 2 mu into dl by L. This is supposed to be the fifth equation. So what you have seen here, we started with r is equal to rho L divided by A. Then we supposed to differentiate this equation. So in this case we just assume one particular term is variable and all others are constants. So we have L by A, we are differentiating rho or d rho, rho by A we are differentiating dl, and rho L we are differentiating A. And you know that differentiation of 1 by A is supposed to be minus 1 by x square. The differentiation of 1 by x is minus 1 by x square. Now dr by r, so every term we are supposed to divide by r, and r equivalent to rho L by A. So we substitute this equation, we end up with an equation d rho by rho plus dl by L minus dA by A. That is supposed to be dr divided by r. This is one of the equations here. Now we know that area of, cross-sectional area of like a circle, area is equal to pi d square divided by 4. Pi d square by 4, where d is the diameter of the circle. Now dA is equal to pi by 4 into 2 into 2d into dd. Can be also considered like dA by dd. So if you say dA by dd, we are going to differentiate A with respect to d. So dA by dt is equal to pi by 4 into 2d. So dA by A, so you have to get, divide this particular equation by A, pi by 4 into 2d dd, pi by 4 d square. If you simplify, you will get 2 into dd by d. So if you substitute that value here, dr by r is equal to d rho by rho plus dl by L minus, instead of this we are supposed to have minus 2 into dd by d. Now we will recollect the equation as we said before, the Poisson's ratio. Poisson's ratio is connecting between change in diameter to the change in length, and we can find out the value of del d by d or dd by d, that is equal to minus mu into del L by L. This value we are supposed to replace in this particular equation. So already we have this equation with a minus sign, and because of the minus from the equation 4, it is going to be plus, so we will end up with an equation 2 mu into dl by L. Okay, so we have this equation. So in this particular equation, d rho by rho is single term, but dl by L is common, so we can write this equation as 1 plus 2 mu dr by r is equal to. So we just divide this equation by dl by L. If you divide that equation by dl by L, this will give you the gauge factor as we discussed before. So d rho by rho divided by dl by L plus this dl by cancel, we'll get an equation 1 by 2. So this equation is nothing but the gauge factor equation. So here, if you look at the equation, if you expand this equation again, rewrite the equation 1 plus, then we will have 2 mu plus d rho by rho divided by dl by L. So now we have our equation. If you rewrite, the gauge factor is equal to 1 plus 2 mu into 2 mu plus d rho by rho divided by dl by L. So this part 1 is nothing but the change in resistance due to the due to change in the length. Already we found it, del L by L, that form. This is the dr by r because the change that has happened with respect to area. Whereas this part, d rho by rho divided by dl by L, which is the change due to piezoresistive effect. And most of the cases, this value will be very, very small, because the d rho by rho, the change in specific resistance with respect to rho, is very, very small or almost negligible. So this particular equation can be simplified as the gauge factor is equal to 1 plus 2 mu. So here mu is the Poisson's ratio. And if you see practically the Poisson's ratio, that is normally ranging from 0 to 0.5. So if it is Poisson's ratio, if you look at the structural materials, 0 to somewhere around 0.5. So if you take the upper value, lower range, if you are substituting 0, so you end up with the gauge factor is 1. And if you're going to substitute 0.5, it's going to be 1 plus 1, which is going to be somewhere around 2. So depending upon this Poisson's ratio, you may have the different value of the gauge.